Hello and welcome to our presentation on a paper by the AI research and deployment company OpenAI with the title Hindsight Experience Replay by Andrzejowicz et al., accessible via this link here. We are Daniel Lederer and Daniel Hebenstreit from Group 31 of the Reinforcement Learning KU. The first part of this presentation is primarily concerned with the description of the method presented in the paper, which is called Hindsight Experience Replay, abbreviated HER. The second part then deals with the performed experiments and the analysis of the results carried out by the authors. A major challenge in reinforcement learning is to design a reward function that is suitable for the given problem. This reward function should not only reflect the given task to be accomplished, but it should also guide the policy optimization. In many practical tasks, the development of a well-defined reward function requires complicated reward engineering, expensive tuning, and domain-specific knowledge. In many situations, this is not even possible, since often it is not known how good a behavior of the agent might look like. This usually results in sparse reward signals, such as binary signals that only indicate whether the task was completed successfully or not. However, with this simple reward system we may encounter slow or non-convergence in more complex environments. This common problem, with great practical importance, has given the authors the motivation to develop HER, that is intended to handle this issue as best as it can. Imagine you want to learn to play ice hockey and you are currently in training. You try to shoot the puck into the net. You hit the puck, but you shoot too far to the right and miss the net. Consequently, you learn to shoot further to the left relative to your current position on the field in order to hit the net in your next attempt. We humans are capable of achieving a similar learning success from a bad result as we do from a good one. But a standard reinforcement learning algorithm, if it missed the net, it will simply conclude that the sequence of performed actions did not lead to success. It will learn little or nothing. It will be ideal if the agent considers the situation in the same way we humans do, namely that this sequence of actions will be successful if the agent had shot more to the left and it learns this. With HER, exactly such a learning behavior is realized in the reinforcement learning algorithm. In HER, we enable any off-policy algorithm to do the exact reasoning humans do by not only using the current state as input for the neural network, but also adding a goal state as additional input. The central idea is to use samples from the replay buffer with additional different goals than our original one. So for a given episode, a set of several additional goal states must be defined. This results in more trajectories with more goals that leads to higher rewards, and as a consequence, learning becomes easier. In the long term, the algorithm then also learns to reach the original goal more easily and faster. With HER, sampling efficiency is improved, and most importantly, learning becomes possible even under the circumstances when the reward signal is sparse and binary. The HER algorithm can be described as follows. The following is given: an arbitrary off-policy reinforcement learning algorithm, such as DQN, then a strategy S for goal sampling for experience replay, and a reward function. For each episode, we do the following. We sample an initial state and a goal and simulate the episode. Using the behavioral policy from the chosen reinforcement learning algorithm, and with the current state and the goal, we sample an action. Then we execute this action and observe the next state. After that, again, using the policy, we sample the next action and so on. Then, after the simulation of the episode, the following is done with the collected data. We take the current reward from the reward function depending on the current state, the action and the goal, and from this we create a state transition of these information here and store the transition in the replay buffer. Afterwards, we sample a set of additional goals for the replay given the current episode using the strategy, and this strategy here, this choice must be well made for the given task. And then we create further state transitions from this, similar as before, but now with the other goals instead of the original goal, and again store the transitions in the replay buffer. And so in the replay buffer there are not only the state transitions with the original goal but also with the other goals. After the procedure above, the optimization phase follows in several steps. In each step we sample a mini batch from the replay buffer and perform optimization using the off-policy reinforcement learning algorithm and the mini batch. Let us discuss an example where we show how the herd technique is applied. Given is a bit flipping environment with the state space here for a certain integer n. A state is thus represented by an n-digit binary number, for example here. The action space is defined as this, and where the execution of action I flips the if bit of the state. And at each episode an initial state and a goal state are sampled, and the reward function for a goal, a current state and an action is defined as this here. So we have a binary reward signal that is -1 whenever S and G differ, otherwise it is 0. Then when simulating an episode with the goal state G, the states S1 up to St without G are observed and the corresponding transitions are stored. In addition, we store these transitions again, but with the difference that the goal state is now St instead of G. Sure, from these additional trajectories we cannot learn how to achieve G, but instead we can learn how to achieve St. With this Herd strategy, at least half of the replayed trajectories experience a reward other than -1, which makes learning easier. It is remarkable that applying Herd in combination with deep neural networks, the agent can even learn to reach G, even though it never observes G during training. And finally, this figure compares the performance of standard DQN with the additionally applied Herd technique in this specific environment. We can see that standard DQN can only solve the task for n smaller 30. It fails to learn for larger n, since in this environment the state space becomes too large to be explored widely. In this case, only the rewards of -1 are observed. On the other hand, DQN plus Herd can easily solve the task for n up to 50.
In the second section of this, I want to have a look at the experiments, at the results, and the conclusion. And first off, I would like to introduce you to some questions which you might already have and their answers. So let's dive right into it. And what you might wonder is, how do we even choose the additional goals? So because before we have heard, we have this experience replay buffer, and we sample from this a second time with a different goal. But how would we choose this goal? And they introduce 4 methods. The first one they call final, where the goal is the last state of the environment. There's episode, where they use the case states, where they just use case states of the same episode. There is future, where they use case states of the same episode as a goal that appeared after the current state. So what that means is you sample from it and you take the steps, you take some state as goal that was after the sample you've taken, which happened in the same episode. And also there is random, so in random you just choose arbitrarily whatever state you want as goal. So now probably 2 more questions have come up. The first one, how do we choose K? And the second one, does this even improve performance? Because we haven't proven it to you yet, but now we would like to do this. So they did some experiments in a physics engine where they have a robot, as we can see on the top right corner of the screen, which is supposed to push a cube onto a red dot, which is supposed to slide, which is the second row, the cube onto a red dot. And by sliding the mean, they just hit the cube with the robot's arm forcefully, such that the cube slides onto the red dot. And lastly, in the last row, we can see that the robot is supposed to pick up the cube and place it onto the red dot. So we have three quite different tasks. And they trained all of these tasks with different versions with different algorithms actually. One of them being DDPG, one of them being DDPG plus count-based explorations, and DDPG with 2 different versions of her, the final and future version, which we introduced on the last slide. So now let's have a look how well this works. So we can see the dashed line is the DDBG, the green line is DDBG plus count-based exploration, blue is DDBG with our first Hindsight experience replay method, which is final, and DDBG with future. So we can see for all these cases that the dashed line did not work, so plain DDBG did not work in 200 epochs. We can see that the green line worked only during the sliding tasks. It didn't work too well, like 20% success rate, that's not too good. But you can see that the right and blue lines show quite a good success rate for all of the tasks, sliding being the hardest of them. But well, okay, so apparently this works for different tasks, which is great, so nice. So let's answer the question with the K, how we choose it and how this works for the different versions. So once again, here I would like to introduce you to the plot, to the figure on the right top side of the screen. So on the x-axis, we have the number of additional goals used to replay each transition, which is just our number of K. And on the y-axis, we have the highest success rate for the top row and the average success rate for the bottom row. And once again, we have our three tasks, pushing, sliding, and pick and place. So what we can already see is that the dashed version is once again at the 4. This time, dashed version just being no Hindsight experience replay. Then we have the final version in blue, random in purple, green as episode, and red as future. So we can see for pushing, all of them had the highest success rate, but regarding the average success rate, red worked best. We can also see the difference between the different Ks is not too large, at least for K equals 2, 4, 8, and 16. Yeah, but apparently for the red one, 4 and 8 worked best. Also in the sliding task, red worked best, at least for K equals 4 and 8, but also green did not work too bad. Blue also, we don't have K with the final version because we just use one episode. We just use the end of the episode, right? And then we have pick and place, where red and green and blue, all of them worked very well. And once again, we can see that red kind of is at the top. So red is everywhere at the top, or at least as good as the others for K equals 4 and 8. So these are quite some nice results. Yeah, and so let's move on to our final slide, which is the thoughts and conclusion. So to sum it up, Hindsight experience replay enables any off-policy algorithm to learn from sparse and binary rewards. So this is really nice because we don't have to do any reward shaping anymore, which kind of lifts the weight off our shoulders, right? And also their experiments showed a nice success rate on a variety of tasks in a simulation, and then also they deployed this on a real robot, and even there it worked fine. So these are some quite good results, and we personally consider this as a breakthrough. Also, what we would like to mention is why we think this is quite great is because we think reward shaping can be a really hard task. Just, for example, in this course where we had the mountain car environment, we have to drive a car up a hill. Given the velocity and position of the car, this wasn't really doable in a bearable time without reward shaping. And when we tried reward shaping at first, this did not work too well because we didn't know how do we translate position and velocity in a way that he learns this. So we had some tries, and it was kind of a bit annoying to get it to work, but finally it did. But it's nice if we could just use Hindsight experience replay to not do this. So we do like the results, and I hope you can use them in the future. Thanks for your attention.